In this video, I'll be finishing up the section 3.1, problems 7 through 11. This is still a section where we're looking at the definition of a derivative. For the seventh problem here, there's really not much to it. It wants us to find the equation of the tangent line at 3f of 3, and then it tells you that f of 3 is 10, and where f prime of 3 is 3. Well, in order for an equation for any line, you only need a point and a slope. So in this problem, they've already told me that f of 3 is 10. So I have the ordered pair, 3, 10, and I know that the derivative at 3 gives me the slope at 3, which in my case, well, the slope at 3 is 3. So I use that information in order to create a line. I use the point slope formula. Y minus y1 becomes y minus 10. The slope, which is the derivative, 3 times x minus x1, x minus 3. Then at that point, it's just a simple case of distributing the 3 on the right-hand side, and I get y minus 10 is equal to 3x minus 9. And then add 10 to both sides. You get your final answer of y equals 3x plus 1. Now, if you're like me, you're thinking, well, that was not a very fun problem. I didn't have to use the definition of a derivative at all. I know, I'm not sure what they were thinking there. The next one is better. It asks us to look at the function f of x is equal to 25x cubed. And then we're interested at when x is 1, it'll ask us the derivative at 1 and then define the equation of the tangent line at that point. Okay, no problem. So the derivative, in order to do the derivative, I use my limit definition of a derivative. Since I knew I'd be plugging in x equals 1, I just kept my limit definition in terms of x. Remember, this is the exact same formula as f of a plus h minus f of a over h. It just keeps your answer in terms of x instead of putting it in terms of a. But either way, it worked the exact same way. I can say, well, f of x plus h, this is, and again, remember the limit as h approaches 0 has to be part of it. Then I can say, well, it's going to be 25 times the group x plus h cubed minus 25x cubed all over h. And then you can say, well, all right, using the Pascal's triangle, I know x plus h cubed, that's going to be h cubed plus 3x squared h plus 3xh squared plus 1 h cubed. Now we're distributing a 25 through that group. You can see I've done that here. The 3x cubed becomes, the 1x cubed becomes 25x cubed. Multiplying the 3x squared h by 25 gives me 75x squared h. The 3xh squared becomes 75xh squared after distributing the 25. And then the last term, h cubed, when you distribute the 25, you get your 25h cubed. Now, we have all of that after it's expanded out, minus f of x, which is still minus 25x cubed. Every single solitary time, the terms of f of x plus h and f of x must cancel. Well, this is no exception. Those two terms do cancel. Also, every single solitary time, the terms that do not cancel always have a common factor of h. So you'll see in the very next step, first thing I did, I knew I could factor an h out of what's remaining. I do that, and I'll be left with h times 75x squared plus 75xh plus 25h to the second. Now notice, I could have factored out more than h, but it's probably best to only factor out the h because the whole point in this problem is you needed to cancel a factor of h with the denominator. You can't allow this limit to approach 0 while there's still a factor of h in that denominator. So from this step to this step, I'm eliminating the h, or as I like to say, I'm eliminate h. And then I can say, oh, cool, then this is the limit as h approaches 0 of that three-term expression up here, 75x squared plus 75xh plus 25h squared. You allow h to go to 0, your second and third term drop out, and you're just left with 75x squared. So I know that the derivative, and I've shown this algebraically now, the derivative of 25x cubed is 75x squared. Well, they wanted us to evaluate that derivative at 1. So clearly, when you plug a 1 into that, you'll get a 75. Now, they also wanted the equation of the line at that point. So I said, well, in order to get an equation of the line, I would need the point. What I did is I plugged a 1 into f of x up here, and clearly that would be 25 times 1 cubed, which is just 25. So my ordered pair is the ordered pair 125, and I have a slope of 75. Plug that into your point slope formula. Y minus 25 is equal to 75 times x minus 1. That's where all of that came from. And then I distributed the 75 on the right-hand side, added 25 to both sides to get to my final answer of y equals 75x minus 50. So pretty cool problem there. Not too bad. Up next, one that's very similar to it, we have f of x is equal to 5x to the negative 1, and we're interested in the slope at x equals 3. So I need to find the derivative of this, and I'll find that derivative algebraically. And then once we find the derivative, which gives us the slope of the equation at x equals 3, we can then find the equation of the tangent line at that same point. Okay, so here's what I did for that one. First thing I did is I wanted to recognize 5x to the negative 1. That's the same thing as 5 over x. This is a rational function. Now, in our notes for this section, I did rational functions with the other definition of the derivative. We had this one in our notes where I did 7 over x plus 2, and I used f of x minus f of a over x minus a, the limit as x approaches a. You could certainly do that in this problem too. Any of the derivative definitions will always work. I almost wish I would have chosen the f of x minus f of a over x minus a, limit as x approaches a, because it works a little bit better in these problems, but either one always works. I was just doing a lot of the x plus h's and a plus h's, so I kind of got in the habit of doing that for this problem. So I can say, well, okay, for this rational function, I can say, well, the derivative of 5 over x is going to be f prime of a is equal to the limit as h approaches 0, f of a plus h minus f of a over h. That is the definition of a derivative at the x value a. So I can say, well, okay, f of a plus h. What do? I plug in a plus h wherever there's an x. So I have 5 over a plus h. And then minus f of a, that's just minus 5 over a, where you plugged in an a for h. Sorry, an a for x. Now, of course, all of that numerator is over your denominator of h. Whenever you look at this expression, it should be very evident what you need to do to simplify. Now, obviously, I can't evaluate the limit until I'm able to get rid of that h in the denominator. But before I can even worry about that, I need to simplify the compound fraction here. I don't want to have fractions inside of a fraction. So I multiply by the least common denominator of all denominators in there. So I can say, well, I need to multiply by a and by a plus h. That's what I do in my next step. I say this same limit, multiplying the numerator by a and a plus h, multiplying the denominator by a and a plus h. Now, please do remember that terms that you're multiplying by must multiply the numerator and denominator, but I know I want to leave that denominator factored because the end goal is I must cancel out an h. So you'll see from this step to this step, I have h times a plus h times a in the denominator. In my numerator, if I multiply these two terms times the first term here, the a plus h cancels, but I'll still have 5 times a left over. That's where that came from. Then I'll have minus 5. This a will cancel out that multiplication of a, but you're going to have minus 5 times the group a plus h. Okay, so now we'll have 5a minus 5a. Please remember the terms of f of a plus h and f of a always cancel, never combine. Your terms of 5a here certainly do cancel, but you'll also have a minus 5h that doesn't cancel. You might also recall what I said in the last problem. Any terms that don't cancel must have a factor of h. Well, there's only one term that didn't cancel, and it certainly has a factor of h. So we can say from this step to this step, I can eliminate h because I have a factor of h in my numerator and denominator. That leaves me the limit as h approaches 0 of -5 over a times a plus h. Can I take the limit as h approaches 0 now? Certainly. If you do, that denominator is just a times a plus 0. That's a times a, or a squared. Your final derivative answer that we found algebraically is -5 over a squared. That would be the derivative at any value of x equals a. Well, the problem asked us for the derivative at 3. So I can say, well, this is the derivative at any value of a. I just need to plug 3 in for that value of a, -5 over 3 squared, that gives me -5/9. Now, if I need an equation of a tangent line, which I certainly did, I can say, well, I already know the slope. I need to know the point. If I plug 3 into the original function, I get 5 over 3. So I know my ordered pair is 3 and the y value is 5/3. So remember, you have to plug 3 into your derivative to get the slope, but you have to plug 3 into your original function to get the y value for your ordered pair. So I have my ordered pair, 3f of 3, my slope of -5/9. I plug that into my point slope formula, and I get the y minus 5/3 equals -5/9 times x minus 3. I distributed the 5/9 on the right, and then I added 5/3 to both sides. And in this case, it gave me 5/3 plus a 5/3 for a total of 10/3. And you can see my equation of the tangent line was -5/9x plus 10/3, which was precisely what Achieve wanted for that problem. The next two problems did pretty much the same thing. The only slightly annoying thing in this one is they put it in terms of t when we're used to doing it in terms of y's and x's, but no big deal. So for number 10, they wanted to know the derivative of this function evaluated at -4. All right, so again, they gave me a rational function. And again, I'm using the f of a plus h minus f of a over h formula. You could have just as easily used the f of t minus f of a over t minus a formula as t approaches a. But this one will always work as well. So I can go in and say, all right, if I use this derivative definition, how does it apply to this formula? Well, what are you going to do with f of a plus h? Everywhere there's a t, you're going to put an a plus h. So that becomes 5 minus the group a plus h. I went ahead and distributed that to 5 minus a minus h in the denominator of that 4. And then we have minus f of a, which is just going to be 4 over 5 minus a. You're just substituting an a for the t. Now, all of this is over h, and it's inside of a limit as h approaches 0. So you say, okay, the end goal is to get rid of that h in the denominator. You can't do that until you can simplify the compound fractions out of the numerator. I multiply by the least common denominator, which is just both of them. 5 minus a minus h times 5 minus a in both the numerator and the denominator. Please notice, in the denominator, I leave it factored. You certainly do not want to distribute the h through those groups because we know it has to cancel out in the end. Everything I'm doing in the problem, it's with the end goal of I need to get a factor of h in the numerator to cancel out that factor. Okay, now, when I multiply by this least common denominator in the numerator, the first term, the 5 minus a minus h cancels, and I'd be left with 4 times 5 minus a. That's where that came from. Then we have minus 4. What happened to the 5 minus a in its denominator? It canceled with that 5 minus a. But then you still have minus 4 times the 3-term expression, 5 minus a minus h. Now, from this step to the next, all I'm doing is distributing the terms in the numerator. I get 20 minus 4a, and then minus 20 plus 4a plus 4h. Again, it should never be a surprise when you start saying, hey, terms are canceling. Terms will always cancel. If you start getting something like a 20 plus 20, you know you've made a sign error. They will never combine, always cancel. -4a plus 4a cancels. Gorgeous. And so then you can say, the only term remaining in the numerator that didn't cancel out is 4h. Should I be surprised that it has a factor of h? Nope. They always have a factor of h. So you can say that factor of h can eliminate h with a denominator, and then that's going to leave you, the only term left in the numerator is 4 over those two terms in the denominator, the 5 minus a minus h and the 5 minus a. Now, what are we going to do at that point? Once you cancel out that factor of h from this step to this step, you know you can evaluate the limit. So from here to here, I'm looking at this and saying, well, what if I let h equal 0? Then this first group is just 5 minus a times the second group 5 minus a. Well, 5 minus a times 5 minus a is better written as 5 minus a quantity squared. And so then I have my final derivative f prime of a defined as 4 over the group 5 minus a squared. Now, if I need to evaluate that at -4, and I certainly do, in order to answer their question, I can just plug that in. I have 4 over 5 minus a -4. Well, I have to simplify that inside portion first. 5 minus a -4, that's going to be 5 plus 4 is 9. But then that's inside of a group squared, so I can say, well, 9 squared is 81. So now here you can see I have my slope of 4 over 81, and that's the derivative evaluated at -4. So I got the first part. All of that was just to get the first part of this problem. But now the second part of the problem is really quick, because it's just wanting the equation of the tangent line at this value t equals 4. So I could say, okay, I'll go back to this sheet now. This is where I continued the problem on the next page. I've already found the slope. In order to find the point, I needed to plug -4 into your original function. So you have 4 over 5 minus a -4 gives me 4 over 9. And so then I can say, okay, I already figured out my slope in the first part. Now I figured out the point. I take that slope and I take that point and I plug it into the point slope equation. Y minus 4 over 9 is equal to 4 over 81 times x minus -4, which gave me x plus 4. Now, here's where I made a slight misstep. This problem was not in terms of x's and y's. I just get so used to thinking of the point slope formula in terms of x's and y's, I felt more comfortable doing it that way. So I went ahead and got my answer, y in terms of x, and then I put it back into their terms of t. So I said, well, technically this problem was in terms of t, so once I got that, I changed it to my terms of t. But before I got to that, I distributed the 4 over 81 and got 16 over 81. I had to add 4 over 9 to both sides, so this was just a nice arithmetic problem. I said, well, I'll have to multiply the second one by 9 over 9. That'll give me 36 over 81. 36 over 81 plus 16 over 81 gave me 52 over 81 for the constant, plus, of course, the slope times x. And I had my final answer in terms of y and x, but they want the answer in terms of t. And in fact, you'll see it took me 3 answers or 3 times to work this problem. I never did anything wrong. Well, yeah, I guess technically I did. I kept on putting this in as an answer. And then I thought, well, maybe they want decimals instead of the fraction. So I tried that. And then I realized, no, John, they just want it in terms of t like it was supposed to be. So please make sure you put that answer in terms of t there. For the last one here, number 11. So it gives me a radical function, which is pretty cool. F of x is equal to the square root of x plus 18. It wants to know the derivative at 1, and then it wants to know the equation of the tangent line at that point. No problemo. So let me go ahead and make this a little larger. In this problem, if I was saying, well, I have this square root function here, the square root of x plus 18, I chose to go ahead and use the other definition of the derivative in this case. You could stick with the f of a plus h minus f of a over h. It will lead to the same answer. I just think it works a little bit nicer with this one. So I said, well, my other limit definition of a derivative is that the limit as x approaches a of f of x minus f of a over x minus a. Well, in this case, this is equal to the limit as x approaches a of f of x. It's just your function minus f of a. Well, it's your function evaluated at a instead of x. So the square root of a plus 18 all over x minus a. Now, I know that that factor of x minus a must cancel in that denominator if I'm ever going to allow x to become a. Right now, I can't because I'd be dividing by 0. In the same way, in the other problems, you have to get rid of the h. You have to get rid of this x minus a. Now, as soon as I see the square roots in the numerator part of a two-term expression, I know to multiply by the root conjugate. That's what I do. It's the same two square root terms with the opposite sign in between, and you have to multiply by that in the numerator and the denominator. Please make sure to carry that down and multiply that x minus a by that conjugate in the denominator. Do not start distributing through that group. Remember, we're trying to cancel that x minus a out. So the denominator needs to be left factored. My numerator, though, and again, remember, this is all still inside of a limit as x approaches a. In the numerator, we know that whenever we multiply by a conjugate, it's really just the first term times the first term, which any square root times itself is just the group of what's on the inside, x plus 18. The middle terms always cancel, so it'd be pointless to worry about them. But then you'll have the last term times the last term. And then we can say, well, it's going to be a negative times a positive, so we know it's a minus. And then the root of a plus 18 times the root of a plus 18 is the group a plus 18. And I emphasize group, parentheses there, critical. Also, it'd be critical if you remember when I said that the terms will never combine. Well, what if you forget the parentheses there and think, ooh, 18 plus 18, I'm going to put a 36 over here. You should know it never happens that way. Terms always cancel, never combine. So I can say, okay, yep, terms are canceling. 18 minus 18, I can eliminate those. And I can see, gorgeous, I'm going to have an x minus a remaining in my numerator, which is gorgeous because that's going to cancel out that x minus a that I needed to cancel out in the denominator. So in this step, the x minus a's goes aways, as I would say, or is I would say, as I would say. The x minus a's goes aways. And then I can say, well, when that x minus a goes away in the numerator, I'm just left with a 1. So I'll have the limit as x approaches a of 1 over the remaining term in the denominator, which was that root conjugate we had to multiply. Remember that x minus a factored out. So I just have this down there. And then at that point you say, can I take the limit as x approaches a? You bet we can. Everywhere you see an x, you need to put an a in its place. And you would have 1 over the root of a plus 18 plus the root of a plus 18. The way we add roots is to collect their coefficients. So you say, well, that's just 1 over 2 on the root of a plus 18. Gorgeous. We have our algebraic definition of a derivative at f prime of a. Our problem asked for the derivative at 1. So I just said, well, plug a 1 in for a. You'll get 1 over 2 on the root of 1 plus 18. That's 1 over 2 on the root of 19. So now I have the equation of the slope. I needed the tangent line. Well, the tangent line is also at the point 1. I needed the y value. So I said, well, the y value is just going to be the square root of 1 plus 18, square root of 19. So 1 was very easy to plug back into the original curve. I get my point. I already had my slope for my derivative. And then I can say, let's plug this into the point slope formula. And I can say, well, all right, that's y minus the root of 19 is equal to the slope, 1 over 2 root of 19 times x minus x1, which is x minus 1. At this point, I distributed the 1 over 2 root of 19 to both sides, and I knew I would have to add this plus the root of 19 on the right-hand side. Just to make the answer look nice, I thought, these two constants would be better written as one term. In order to do that, I need to get a common denominator of 2 on the root of 19. So I thought, well, then I would need to multiply this numerator by 2 on the root of 19. And I thought, well, the root of 19 times the root of 19 is 19 times the remaining 2 gives me a 38 over 2 on the root of 19. So I can say, okay, this term in red is the equivalent to that. Now it has a common denominator. It's going to be 38 minus 1 over this denominator of 2 on the root of 19. That's where I got my final answer there of y is equal to 1 over 2 on the root of 19 times x plus 37 over 2 on the root of 19. That was a glorious problem there. I really liked that one. Hopefully you do too. And you can see that that is precisely the answer that Achieve wanted for this one. Now, I will readily admit working the problems on Achieve in this section takes some of the fun out of the definition of the derivative problems. I would much rather do the glorious algebra that's required in some of these definition of a derivative problems that we really can't input into the Achieve software. So it limits our fun a bit in this section. Now, in the next section for 3.2, we're going to actually start some derivative rules. So we'll learn the shortcuts to some of these things that we did in this section. And I think a lot of you will like the shortcuts a bit better. But it will start being rules that you have to memorize in each of the sections from here on as to how to do it the shortcut way. All right, guys. Hope you're doing well. And let me know if you have any questions, as always.